The next hour, I'd like to talk about the cell processor. And first, I have to make a warning, and second, I have to give you a disclaimer, because first, the warning, this is going to be a technical talk. So everybody who's not expecting a technical talk and does not know what an assembler is, I think you won't enjoy it. So the second fact, the disclaimer, it's mainly about that I didn't invent the cell processor. It's, yeah, you know, maybe. It's invented by this STI consortium. And yes, all these facts I'm naming are available on the net. And I hope I'm not going to tell anything else because I signed the NDA with IBM. And yeah, we'll see. Okay, so just one sentence to my background. I'm working in at the Technical University of Chemnitz in the Department of Computer Science, chair of computer architecture. We are caring for scientific computing and calculating all kinds of scientific problems, for example, quantum mechanics, and try to accelerate these calculations. So the cell processor will be great for this task. But I think you're not very interested in scientific computations. You're interested in other kind of computations, for example, computing keys or computing certificates and all this stuff. And I think you can be quite sure the cell processor will also compute keys if you want it. And very fast. So, to my outline. Basically, there are 5 points, 4 on the slides. One is a demonstration. So, sorry, the demonstration is just a simulation because the cell processor is not yet on the mass market. And yeah, but there's a simulator provided by IBM which can be downloaded by everybody, and I try to show you a very small example of the power of the cell processor. I hope that we have time at the end, but we'll see. So the first point is general vision. It's a short introduction. Why is cell processor? Why are we going to do this new approach? Why aren't we sticking with the x86 architecture? Or at least why is IBM doing this? The second one is the whole part, the main part of my talk. It's the cell architecture. That's going to be hardware details and how you can leverage these hardware details for your specific task of maybe computing some keys or something. I don't know. The third point is very, very short one because the cell programming is basically up to you. So I can't tell you what you're doing with this cell, but I can tell you about the architecture, and you can experiment and program your own programs and run them on a simulator. And if you have the cell, then you can run them on the real cell. Okay, the fourth is just a summary, and the fifth one, if I have time, the simulation. Okay, basically the research started in 2000, so I think many of you know. So Sony, Toshiba, and IBM founded a new research group to develop a new kind of processor. It's basically called STI, Sony, Toshiba, and IBM, this consortium. So every member of it brought something special. So Sony brought the PS2 architecture, which is also very interesting, but unfortunately supports only single precision calculation, and so for scientific calculations not very suitable because scientific calculations needs double precision here, you know. Toshiba has memory experience, and they're producing memory chips and these RAM bus, and they need chips for their TVs, for HDTV. If you've ever been to Japan, for example, everything is HDTV there, and it's very compute intensive, and so you need these chips, cheap new chips. IBM has technical knowledge in processor manufacturing. Of course, I don't have to tell you. They invented nearly everything through this out-of-order execution, this Tomasudo logic, so cache reuse, and everything. Yes. That's another thing. For example, it's also very interesting that the cell design or approach maybe is very old. It's by Cray. Okay, but it wasn't copied. They brought it to a new level. But I'll come to this later. Okay, but altogether they invested billions of dollars. That's really a big investment. They made a totally new research facility and built up everything from scratch. And yeah, they wanted to propose a high throughput multi-purpose processor. High throughput because of this new multimedia design. So everybody wants to support multimedia, this HDTV and all this stuff. And for, of course, video games. So that's also things where you need very high throughput. Yep. And you have several problems with current architectures to support these high throughput. Yeah. This is, for example, the memory latency bandwidth gap of the von Neumann principle. It's a very huge problem. You can't get around it. You just have to invent a new architecture to get around it. And that's basically this thing. You have this instruction latency gap, which is very funny because an instruction just gets into the processor and needs very long time to be actually processed because you have all this control logic which cares for your out of order execution and this Tomasulo logic inside the processor for reordering the single instructions, for getting them faster or finding some parallelism in inside these instructions. That's mainly about this out of order execution. They try to find parallelism for in the instructions to compute them in parallel. But this adds an instruction latency because the throughput is higher. It's basically much higher, but the latency is also higher. So a single instruction needs more clock cycles to get through the whole processor. Yeah, and then the old-fashioned x86 architectures is going to be a problem itself. For example, yeah, just remember the A20 gate. Yeah, I don't need to add anything else. Then we have this implicit mem hierarchy. That's also very interesting. Is it a problem or not? It was designed to help. So it was designed to help programmers to get faster access to memory. To these, I'm talking of these layer 1 and layer 2 caches. But actually, now the programmers are designing for this implicit things. So you're trying to imagine what the hardware will do with your code, and you're optimizing for the specific hardware. So that's quite ugly. You could optimize if you have direct access to it. You could optimize in a better way. You don't have to optimize with several assumptions what it's going to do with my code and reordering. But yeah, basically we can discuss very long if it's a problem or not. So I had this discussion with my professor, and it took a very long time. Then we have the longest path. That's basically to determine how fast my processors can be clocked. So if my longest path, so the longest pipeline stage is very long, I have to reload. So we have to imagine that we have to reload every electrons to and from all these transistors into this longest path. And either we take a very huge voltage to put them through, but maybe it will burn, or we just introduce a longer pipeline, a deeper pipeline with very small pipeline stages, and we can shorten the longest path, basically. Yes, that's what Intel did, and we see it's not the best architecture, the net-first architecture with 20 pipeline stages. Yeah, 30, okay. Maybe more, we don't know. And then that's the most important fact. What are we going to do with these millions of transistors we have? Every year, every 18 months, according to Moore's law, the number of transistors doubles. And so what are we going to do with these transistors? We can put more functionality and more functionality, but the problem is to put more, the CPU isn't getting faster with this more functionality. The CPU is just staying at the same speed. Maybe we can introduce more parallelism, but this is also limited. The instruction parallelism is limited. So this Tomasulo logic doesn't scale to infinite, and our problem is that we want to scale to infinite, but we can't do this on a very fine-grained level, so we have to go a level up. That's what I am going to tell you on the next slide, I guess. What can we do? Or what did we do until now with all these transistors? Because Moore's law basically has been there since a couple of decades. And we introduced this superscalar architecture and this Tomasulo logic, which is responsible for trying to find an out-of-order execution, of course, trying to find instruction-level parallelism. This is called ILP, or the buzzword. And yes, trying to leverage it to increase the overall throughput of my CPU. So I think everybody's doing this today. It's done by Intel, it's done by AMD, and of course IBM. And yeah, the second point was to introduce speculative execution, so that we have two branches. Just try to take. I think you all know about this. I'm just going to repeat it, very short. Two branches, take both and just discard any calculations done in the wrong branch when we know the branch decision. So we have hyper and deep pipelining. That's also very interesting. So just two pipelines, and these pipelines are processed in parallel. It's just another kind of parallelism. What we see, it's basically about parallelism. Everybody tries to find parallelism, but the processor is on a very, very, very low level. So the processor sees only the single instructions, and the single instructions, he has to find the parallelism inside these single instructions, and that's going to be a problem, because, as I told you, that's limited. If you're usually programming, you can do 5, 6 instructions in parallel, but a normal code doesn't allow this. And as fourth, we introduced virtual memory and caches. That's what I mentioned in the slide before. And now we're going to see, did it pay off? Did it help us to improve the overall speed of a CPU? Yeah, I have to say partially, because the first thing we reached was high throughput and high clock speed. Very easy, introducing pipelining. Pipelining is also a concept of parallelizing some architecture. So you basically have more than one pipeline stage, and they're just computing in parallel and just processing it. So we shorten the longest path because we just divide it by n for n pipeline stages. To say very easy, more complicated, of course. And we need buffers between these pipeline stages. Yeah, that's going to cost us transistors. So to introduce this new technology, we have to invest transistors. But the overall estimation is that we reached pipelining, we have very high clock rates, but the problems which are arising are actually the pipeline effects. So you have different hazards in a pipeline. There are structural hazards, there are data hazards, and there are some more hazards, but basically the structural hazards are very easy to overcome. So you could just introduce dual port RAM or something, but the data hazards, they will stay. And also the third kind of hazard, the control hazard, will also stay. What can you do? To avoid the control hazard is going to speculative execution. So you're just doing what I told you. So you're calculating two branches and discard the branch which is going to be wrong. Basically this is done by the Itanium processor, the speculative execution. But I don't know any processor which is doing this else. But maybe you can tell me more about this. We see Pat Gelsinger is one of the Intel guys, which is the chief technology officer, where proposed Gelsinger's law. Gelsinger's law basically says that the doubling the amount of transistors is actually increasing the performance only by 1.4. So just check Google for Gelsinger's law and you will find this. I think that's a kind of unofficial, but it really says what I'm going to tell you. So we can double the transistors. We can introduce more and more logic, but we won't find more parallelism in the code. The code is as it is. And so this parallelism isn't there. And what are the processor guys going to do? Just move it up. So we are building a processor. We don't find any parallelism in the code. Just, okay, let's move the problem to the programmer. Let's let the programmer think about parallelism and trying to parallelize things. And that's what they're actually doing today. So they're introducing multi-core. Everybody knows if I have a multi-core, my computer doesn't get any faster. It just has 2 cores, 2 processors. And I have to care of it to make it faster. I have to program parallel codes, or okay, I can run 2 programs, but that's a very stupid approach. I have to parallelize my code to make it run faster, and I have to find it. So they just moved the problem up to me. But the funny thing is, this multicore is also not very nice, because inside this multicore we have again these logic, this Tomasulo logic, this out of order execution logic, which drops down my usage efficiency of the transistors. So we have to think in transistors, or in chip size and die size. That's basically what we're going to do. We're paying die size when we're buying a transistor, because it costs nothing to put, buying a processor, sorry. It costs nothing to put transistors on a die, but the die size costs. And yeah, what are they going to do? Now, the easy approach is multicore. Yeah, that's, everybody does this, Intel, AMD, of course AMD first, then Intel. The second approach is vector processing. I think that's a very old thing. Vector processing was done by Cray, and I think that the first Cray was a vector processor. And it looks a little bit like the cell processor, if we look at it, but the cell processor takes it to the next level. So we have vector units which are going to accelerate our code, but we have to care for programming them. And yeah, basically the same thing as SIMD. We all know that's being in the commercials since 2 years. The LTVAC or MMX or SSE or SSE2 or SSE3 or some more SSE. So we are extending the command set, so the instruction set, the ISA instruction set architecture, with new instructions which are vectorizing our code. So again, the programmer has to find it. There's currently no real compiler which, okay, they're trying to develop some, but I didn't see a really good compiler which really finds vectorizable code in some random program. They're just these mathematical programs which are very easy to randomize, to vectorize, because because they are not random. They're like do loops, and yeah, it's very easy to find a vector inside a do loop, because yeah, it's just a do loop. We can introduce more registers. That's also very interesting. So if I have more registers, I have basically a bigger working set. The processor is working on registers, at least in a load store, in a clean load store architecture. And I think most of our processors, our current processors, are load store architectures. They seem that they're x86, these ugly, oh, you can operate in memory and you can operate on anything else. But yeah, they're translating it. So they have 2 layers, and they have an outer layer and then an inner layer, which is a risk. And the outer layer is just receiving all these high-level x86 commands, translating it into multiple small commands and operating on it on internal registers and something like this. But you have to ask Intel or AMD for this, I don't know. We can introduce explicit SRAM, which is basically the same as more registers, but it's cheaper. So SRAM is not, we can introduce bigger amounts of SRAM. We'll see this at the cell processor. They have a big amount of SRAM, but only, okay, very small amount. It's not small, we'll see. Yeah. Yes, but it's explicit cache. So it's not, cache is something you don't see. Bless you. Cache is something you don't see. It's like it's just working magically for you. It's finding your access. It's using your locality principle for you without managing it or without mentioning it. But this explicit SRAM is just like a scratch board for you, a scratch space where you can program, which you can using by programming, or which the compiler can use. Yes, yes. Okay, and then we can add GPU parallelism. So we all know that the GPUs, today's GPUs are highly parallel, because a task of rendering an image is highly parallel, it's implicit. So from x86 to the future, that's a question mark, because I'm not sure about this. But I think the RISC design is a way to go, because it's easy and it can be very fast. We can clock RISC processors up to several gigahertz, up to 10 gigahertz with no problems, because they're very easy. The CISC design is not that way, but I'm not sure. It depends. The RISC design just moves the complexity into the upper layer, into the software, or we have to care about programming it, and the CISC design just tries to manage everything in hardware. So that's a basic, basic difference. We are going to have in-order CPUs because this out-of-order principle is quite nice to find instruction-level parallelism, but we pay a high price for this. We need all this Tomasudo logic, reservation stations, and all this additional hardware we don't need without it. And actually, Intel did a very interesting, I don't want to say experiment, but yes, this Itanium architecture, you all know. Maybe somebody thinks, or maybe most of you think that it's dead, but I don't think so, because it's a very interesting architecture. The only mistake they did was to introduce it without a background. So the cell is the same. We are going a new way. We are destroying most of the compatibility and going a new way, in a new direction, but we have a background, or they have a background, IBM, Sony, and Toshiba, because they have PlayStation. That's what it's going about, and that's going to be a big success, because yeah, many people will buy PlayStation, but how many people will buy servers with Itanium processors? Okay, he said that it's HPUX is available for Itanium, and yeah, that's going to be better, I think, but we'll see. I'm not sure, because it's just too expensive, this processor, yet. And okay, then we have a system-on-chip design, which everybody's going a system-on-chip design, because basically 2 cores on a single chip is a system-on-chip. And then we can support heterogeneous multiprocessing. Okay, but I have to go on that you can see the demonstration later on. The cell architecture. First patented by Ken Kutaragi in 1999. It's I think the CEO of Sony. And he has a vision. That's a very visionary vision. It's very far away. And just look at this. You have different devices, and you have hardware cells, which is basically a processor processing a software cell. And a software cell is just like a small task. So you want to do something, you pack it into a small packet and send it somewhere in the net, and it will come back processed for you. And yeah, so floating software cells, I think that's written in the patent. And yeah, that's what's on this slide. But we're not in this way, not yet. We'll see if this will come. But maybe, yes, these software cells will be controlled by the government or something, and we are able to process them by ourselves. The cell processor is actually a heterogeneous multiprocessor consisting of 9 cores. And these 9 cores have many abbreviations. So I just want to introduce these abbreviations that you can follow me later on, because it's going to be very abbreviative. The SPU is the synergistic processing unit. So you all know what synergistic means, I think. It's a very funny thing, but I don't know why they call it synergistic. But the second thing is the memory flow controller. So an SPU plus the memory flow controller is a SPE. It's a synergistic processing element. That's basically 8 of these 9 cores. And then we have an additional power processing element called PPE. That's the old legacy thing inside this processor, which keeps up compatibility to the outer world. So it's just running anything. Every program which is running on a PPC 970 is running on a cell processor without any change, because it has this power processing element on it, and it just can process the application as normal. And yeah, put everything together, we have a cell processor, and these are 9 full-blown CPUs. So we buy 1 processor, and we have 9 CPUs, and this processor is not going to be very expensive. So basically, I think this PlayStation will be the cheapest thing to buy a cell processor, but I'll come to this later. Okay, all these elements are connected with the element interconnection bus, and of course, they have an I/O connection to the outer world, or to other cell processors, or to anything else, just to submit, for example, these software cells to other cell processors. And we have a memory interface controller, which of course is interfacing to XDR, because Toshiba. And unfortunately we have hardware DRM, and we'll see how bad it's going to be. I hope we can switch it off. I'm not sure, but because Sony is inside, and I think if Sony is able, if Sony is able to put a hardware rootkit into the cell processor, they are going to do it, and that's maybe this hardware DRM, and so I'm not sure. There's also another very funny thing about Sony and the PlayStation, but I'll tell you later. And the interrupt controller basically routes all interrupts just to the PPE, because the PPE is supposed to do all operating system tasks. So, for example, if you're moving your mouse, the PPE is processing it. It's not processed by any SPU. Effective, it's a network on chip, of course. And yeah, we have this number, 256 gigaflops inside a processor. But yeah, we'll come to this later also. Okay, that's how IBM, so source and copyright IBM, sees the cell processor. Many abbreviations, but basically what I told you. We have the element interconnection bus, interconnecting everything, power processing element, memory controller, bus interface controller, the SPU or the SPE. So then we have a synergistic execution unit, of course everything is synergistic, and a local storage. So there's the first prototype. The first prototype was, of course, produced by IBM, or inside this alliance between Sony, Toshiba, and IBM. It's a 19 nanometer silicon on insulator and has 8 copper layers. It's reminding me of the Opteron, I don't know why. And 241 million transistors and a very small die size. We see 235 square millimeters. And it takes only 60 to 80 watts. And that's amazing, I think, for this power we can get out of it, for this calculation power. And they only enabled 6 to 7 SPEs, but okay, that's going to be normal at the beginning of the production process, because the yield would be very low if we would enable all SPEs. It's just like the like Intel does like every processor vendor does, for example. If something in the cache is broken, just switch it off and sell it at a cheaper price. So it's going to be a Celeron processor if something in the cache is broken. And yeah, that's what they do. And that's also what maybe happens to the PlayStation, but we'll see. And it supports IBM virtualization technology. Very interesting approach. So we can run multiple operating systems on it simultaneously. Like, you know, maybe Xen, and it's Xen in hardware, or VMware in hardware. And yeah, it's operated at 1.1 volt, and it's able to achieve clock frequencies higher than 4 gigahertz. So the prototypic implementation. Okay, now I'm coming to the interesting thing. That's a floor plan of the cell processor. I think it's also copyrighted by IBM or somebody, but I found it on the net. We have the first thing, that's the PPE. That's the PPE, and that's the layer 2 cache. So we see layer 2 cache is quite big. And we have to remember, every square millimeter on this floor plan costs money. So it's not about transistors or something, it's about square millimeters. Okay, that's just a block diagram. And to say something about the PPE, it's not very interesting because it's a PowerPC compatible and runs every PowerPC code. It's a dual-threaded 64-bit power architecture, of course. Dual-threaded, it's this SMT simultaneous multi-threading is like the Intel, how's it called, hyper-threading. So it's some virtual parallelism inside the processor. It has, of course, the vectorized multimedia extensions and is a simple architecture. That's the biggest difference to the power processors, for example, Power 4 or Power 5, because it supports only in-order execution. Why this? We have a very high clock frequency. So we are running these chips at 4 gigahertz. And we can't, and everything is running at 4 gigahertz, the PPE, the SPEs, the bus. And yeah, so we need a very simple architecture with a very deep pipeline. So not as deep as the Intel processor, but still 20 pipeline stages is quite, yeah. Yeah, you told me that you did it as 30. Okay, the current one, yeah. Yeah, but okay, it will have the same problems basically as the Intel Pentium 4 processor. Um, we have 2 instructions issued per cycle. It's not very interesting. Split cache, and it's also, this is basically the part which supports virtualization. Yeah, that's not supported by the SPEs or something. It's supported by the PPE, of course. Yeah, to say overall, it's a simplified power architecture to run at these high frequencies. The synergistic processing element is the thing which is interesting at the processor, at the whole cell processor, because we have 8 of it. It's a very small processing element, but it's just the amount which counts. We also see that it's occupying most of the, altogether, most of the floor plan. And yeah, it's connected with the EIB. And each of it is a fully blown vector CPU. So it has own RAM, SRAM. It's not a cache, so there's a difference between RAM and cache, you know. This instruction set architecture of this CPU is not VMX compatible. So they just invented basically a new instruction set architecture, which is really completely new. So you have to relearn everything. That's not very nice, but yeah, it's very interesting. It has a fixed length. That's also a strict risk approach of this architecture. And yeah, 21 million transistors. That's not being very interesting. But we see that's the storage, the local storage, and that's the calculation entity. And we see quite a lot of storage, and the register file is also quite huge. And we see why. Not on this slide. It's, as I said, as I told you, it's a very, very, very simple processor. So it has no branch prediction or scheduling software. That's all which was achieved in the last years in processor design was branch prediction, scheduling, and out-of-order execution. And they throw it out because they want to get very, very high clock frequencies, and they want to move the complexity into software. They just going a totally different way to move the complexity up and to let the compiler or actually the programmer decide how fast the code will run on the processor. And we have 2 independent, very short, and simple pipelines. I don't know about the real pipeline depth, but maybe you can help me. No? It's maybe not published yet, I don't know. Yes, a very short one. And we can issue inside these 2 independent pipelines 2 instructions in parallel. That's also very interesting because it supports overlapping of memory fetches with calculations. And that's a very cool feature. Basically, every processor has it, but it's explicitly mentioned here. And we can do 1 memory and 1 SIMD computation. Basically, every computation inside the PPE is an SIMD computation. So you're operating all the time on vectors. So it's a vector CPU. It's strictly in order. So yeah, they can't pass each other the instructions. And they all work with a 128-bit compound data. So compound data means that it can be a vector of 4 32-bit integers or 4 32-bit single precision floating point or 2 64-bit double precision floating point, or something else. So like the normal data types we all know. We can process 4 single precision floating point operations per cycle. So it's pipelined, of course. We have a latency of the pipeline depth. And they are not fully IEEE compliant. So that's more or less for the scientific community, because some scientific programs rely on these special IEEE features like not a number or special rounding features. But I think it's not very important for the task of the for the task of the cell processor to just process multimedia data, because yeah, multimedia data is not very demanding in number accuracy or something. It doesn't matter if the pixels is there's a little bit different color or something. You just don't see it. And we see we have 4 single precision floating points per cycle. We assume 4 gigahertz. Then we have 16 gigaflop. And then we have this magic IBM fused multiply add instruction, which is basically doing multiply and add in parallel, so in one cycle. And we achieve 32 gigaflops. So this fused multiply add instruction is something, yeah, I think it was designed for the top 500 list, just to to push the systems up. Sorry, IBM, but we've made several investigations that it's really very, very, very useful for scientific programs, and that's it. So I don't know how useful it will be for designing multimedia or streaming applications, but for scientific programs, it's a very useful command. Then we have unfortunately, a very slow double precision arithmetic, which is nearly fully IEEE compliant, and it's quite slow. And it's also not fully pipelined, and there's also another restriction. You can read everything in the programmer's manual, which is quite thick, I think 200 pages or no, 600 pages. And yeah, for example, after issuing a double precision command or instruction to the processor, the next 6 clock cycles, no instruction can be issued. So it's just blocked for 6 clock cycles. And so they can't give you a direct number for the gigaflops, because it depends how other instructions are going to the pipeline, and because of this blocking. Yes, and we can process, of course, 4 integers per cycle. That's just the normal vector processing approach. And that's a block diagram of the SPU. We have the local storage. It's 265 kilobyte. That's all RAM we have for our programs. So we have to write very small programs. We can fetch more. We can access the whole system memory through DMA. But basically, we have to stick with this 256 kilobyte. And the instructions are also inside the 256 kilobyte. We have this two-way issue, even and odd pipeline. Both pipelines operating on these 128 registers, and yeah, doing all this stuff. So interesting is the distinction between calculating pipeline and memory fetching pipeline. So they're operating in parallel, of course, would be no pipeline. And we can double buffer very, very efficiently with these processors. We can fetch an instruction and calculate the next one. No, we can calculate an instruction and fetch the next data item, for example, then swap buffers, calculate the data item from the previous fetch, and fetch the next one. So that's a very interesting principle in scientific computing, just to overlap computation with the data fetching, and you achieve nearly 100% of the theoretical peak, because you don't stall at memory fetches. Yeah, the memory can be accessed in 120-bit, 28-bit lines. Yeah, that's not very. That's optimized for bulk transfers. And interesting is also registers are layered. There's no distinction between, for example, floating point registers or general purpose registers. Everything can fit into a register, as it is a vector data type. So floating point data and integer data are residing in these same registers, basically. We have no virtual memory or no coherency on the local storage. We have no processing in main memory. So we have to fetch the data item into our local storage. And even more, we are also not allowed to, or we cannot process on the local storage. So we have to fetch the data item into the registers, because it's a RISC design. It's a strict load store architecture, as we all know. Then, yeah, the DMA, I already told this. The MFC, basically the memory flow controller, connects to the EIB and does some additional tasks, like the MMU in the traditional x86 architecture does. So it holds a small page table, and well, this is going to be a little bit more complicated, because it has no access to the global page table. So basically the PPE has to tell the SPU for the actual running process, which pages it's going to access. But that's a programming detail, it doesn't matter here. And it does synchronization, because we have a parallel system. basically we have a parallel system on a chip, and we have to synchronize between these tasks, units. Okay, how are we going to program it? Typically, we are going to spawn user-level threads. So we just run a program. It starts at the PPE, and then it spawns off a thread on the SPE. So yeah, the thread is not like a normal thread like we know, because it has a different binary. They have a different instruction set, so we need different binaries. So we just tell the PPE to load a binary into the local storage of some SPE, and then the SPE to execute it. That's how it works. And we have that's going to be very complicated. I tried to program it, and that's awful at the beginning. But IBM is very kind and gives us an IDL tool. It's called Interface Description Language, and it supports RPC programming. So basically, we can define a small function which is going to be on the SPU, and which we are going to offload. And we just use this IDL tool, and it does everything for us. It defines the interface. It cares for the loading of the instructions and data to the PPU. No, not PPU, of course not. SPE, sorry. And it triggers the SPE to execute the program and gets all the data back to us. That's very, very nice, but also a little bit limited. I'll show you when I have time. We can do, of course, assembler programming and also C and C++ programming. We are provided with several C and C++ intrinsic functions. That's very nice. So we don't have to use the assembler, inline assembler to use the special features of the SPU. We just have functions like SPU add, SPU mul, SPU diff, which acts on vectors, vector data types. So we have new data types. We just pack your data in, and yeah, I'll show you a program later on. And we have no access to the system control table, I told you. And the local storage is unprotected and untranslated, so we can't implement an operating system inside a SPE, for example. So we can, but it's going to be hard. It's a strict load store architecture. Yeah, okay, I told it. So just a small comparison. This is the Opteron floor plan. It's about 140 square millimeters. It runs at 3 gigahertz, for example, and can issue can finish two floating point operations per cycle. Okay, I'm talking of single precision. And the SPE is down here, and it's running at 4 gigahertz and can finish 4 single point floating point per cycle. So we see it's really fast, and the Opteron is not a bad processor. But if you would compare the double precision, the Opteron would be much better. But I just wanted to show something that's really amazing. And we have 8 of them. Yeah, you have to remember, we have 8 SPEs, and all connected with the element interconnect bus. That's the thing in the middle, which is connected to all entities of the cell processor. It has 4 128-bit wide concentric rings, so the data is just passing around in a ring, and we can transfer 96 bytes per cycle. So you should just try to calculate which data rate we have. So basically 4 gigahertz, and it's nearly 400 gigabytes per second we can transfer on this bus. And it's very interesting that it's a buffered point-to-point ring. So everything is independent. It's not really a bus, it's more a ring than a bus. So if you know SCI, you just send an item to the next entity, and it stores it and sends it to the next if it's not for the entity itself. And yeah, so we have, for example, also a guaranteed bandwidth, because I can just take my slot when I want it, because I'm going to forward the data for others, and it's just up to me if I want to take my slot, I take it. And the SPE, better to say the MFC, so the memory flow controller, has the duty to route the traffic. So it's also very, very scalable. We can add more SPEs as we want, just the latency to reach another SPE increases. but we will see that there are very, very efficient ways to overlap. And so we can see that this latency is not being so important. And we have this guaranteed bandwidth which makes it real-time capable. Yes. Yeah, it's a shift register. It's not like token ring. It's like, yeah, you put from one entity to the next entity, and it copies it to the next, and so on. Yes, yes. These 96 bits. They have to shift it in one cycle from one entity to another, and that's a very nice feature, I think. So, the Flex I/O. It's just to communicate with the outer world. It's also because if you're a computer scientist in supercomputing, one processor is not cool. You need at least 1,000, and therefore you need a Flex I/O to interconnect the processors, for example, directly or indirectly with the network. We have very fast connection, so it's just 60 and 96 pairs in the whole is just important as you see how many pins the processor must have, at least several for the voltage, and at least these 96 pairs to communicate with the mainboard. And we have 7 lanes with 44.8 gigabyte per second outgoing, and 5 lanes with 32 gigabyte per second incoming. So it's a real cool network, I think. And also very nice is that we can connect 2 processors glueless. So while designing the cell, they just were designing a dual cell in the same thinking. So just you put two cells together and you have a dual processor with no cost. You just can add them. It's a little bit like the Opteron here I've written. It's comparable to hypertransport. You have coherent and non-coherent links. Basically, of coherent links, you can build a CC-NUMA architecture, and it's going to be more and more interesting. There's the first dual cell blade available from Mercury systems, which just put 2 cells together without a switch, because they can connect it gluelessly. And you can just put 4 or 8 or more, and you just need a switch on the system. That's like a normal network, I think. It's not published much, but I think it's like a normal network. So then we have a memory interface controller just to access some more memory than our 256 kilobyte. That's connected, of course, to XDR. Also, just look at the number here. I don't have to say anything else. It's 25 gigabyte per second. And funny thing is, why is ECC protected? So it's designed in the cell documents as ECC protected memory. Maybe IBM is going to use it as a server, because I think ECC, everybody knows ECC is not very important for PlayStation, or maybe HD TV, where 1 pixel will shift if some radiation comes. But for a server, it's very important. And yes, I'm not sure, but maybe somebody can tell me at the end of the talk. So they have a conventional protection system, I already told you. They use virtual addresses, and they have no cache. So the memory is not cached. Only the PPE is a cache, and the rest of the system is uncached. What is going to be different in the programming of the cell? So we are not programming at an abstract model like the x86. In the x86, we are programming an abstract language, so like it was designed decades ago to support some very old processors, and everybody just keeps it up, keeps it alive due to compatibility reasons, just not to lose any customers. And it's going to be difficult, of course. I'll show you. And we have the same problems as multi-core, because we have to parallelize. We have to think about this, how to parallelize our code, not the compilers doing it, not implicit instruction parallelism. It's just we have to think about everything. And assembly is available, of course. We are programming it directly. We can program in C. I already told this. We can virtualize the SPEs in the operating system. That's also very interesting. So the the operating system is allocating the SPEs for a specific task. A Linux version is already available which is doing this. It's very nice. And PPE code is usually PowerPC compliant, and Linux was running without any modifications, but it wasn't able to use the SPEs, of course. So there were modifications done to the Linux kernel to use the SPEs, and I think IBM is trying to push it into the mainline kernel, so I think they're quite successful. The SPE code must be self-contained. It's also very, very interesting. So that's like the SPE code is basically a small program which is runnable without anything else. So you just can put it on this small SPE and it runs, and yeah, it processes. And an auto-vectorizing compiler is available from IBM called Octopiler, but I don't think that it's going that good because I didn't try it, to be honest. But I think there's no auto-vectorizing compiler yet which is working better than a human optimizing some code. So basically, all these PlayStations and PlayStation games are, in my opinion, programmed by hand and optimized by hand and written mainly in assembler. So I hope you're also going to do this. So I'm giving this talk that you're going to develop cell programs, you're going to port John to Cell, or maybe other very interesting programs with these programming models, of course. So it's just what you can think of. Job queue to enqueue multiple jobs. You can build a self-multitasking SPE, but I don't know if this is going to be very useful. But you can make stream processing, of course. Stream processing is very, very important for managing these decoding video streams and displaying HDTV and playing video games and all this stuff. Okay, for video games it's not that important because you need to react very fast. You can implement a software-managed cache. It's also very interesting. And maybe MPI, but that's more personal thing for me, MPI. I discussed a long time with the IBM guys, which prefer the shared memory model, but we'll see. So, summary and conclusion. What can we do with the cell processor? Why am I here? I'm just here to tell you about the new processor generation which is going to come, and to encourage you to look at the cell, look at the simulator, and see the power which is behind it. So program your applications like very, very cool demo applications or something, which are going to be run very fast on the cell processor, or yeah, something else. The PlayStation 3 is coming out, or maybe not. We'll see. It should come out this spring, but I think it's very, very short for Sony, and it's very tough for Sony to get it working until spring. And they told that it's going to be only at 3.2 gigahertz. That's not very nice. And it's going even worse because they say we have only 7 SPEs to the programmers which are programming the video games. And that's very interesting because nobody knows why. The first idea was, okay, they're trying to increase the production yield. So they're just switching off broken SPEs like Intel or AMD does and sells them like a cheaper one. But then some deliberations came up that, okay, the production yields are going to be very, very high because the production started yet. I think it's the cell processors in production, and the ramp up phase, how it's called for a microprocessing company, is going to be finished soon. And yeah, then the yield, they could just enable all 8 SPEs, but maybe they're using an SPE for a dedicated rootkit or something. I'm not sure, because it's Sony. Sony is selling the PlayStation, Sony is programming the PlayStation, and Sony is programming the operating system for the PlayStation. This Ken Kutaragi told us that we are going to expect a Linux version, like for the PlayStation 2. So I'm very, very interested in this version, and I would be very happy to see this. But if it doesn't come, then I hope we can manage it to put a Linux on this box. So the second application is server applications. So IBM, basically a good friend maybe, Mercury, thinks that these cell processors is very, very, very mighty, and it's very good on server applications, on servers in general. So they sell a Blade server, which is compatible to the usual IBM Blade Center with 2 cell processors. Fortunately, they have 8 SPEs enabled, so another evidence for the rootkit. And it's running Linux, of course. And yeah, more applications, just find it. So how much time do I have left? Oh, fuck. Okay, sorry. Yeah, I just skip it. Very interesting is that we could beat the world's fastest supercomputer with 131,000 processors with just 14,000 cell processors with dual precision. With single precision, we would just need 1,400. So you see, but unfortunately, this top 500 list, which is ranking these processors, is dual precision. So they just give the problem for dual precision. But you see this, and it's really going to be a very cheap. I've heard about $100 something. I'm not sure. A very cheap processor, which is extremely fast. So you have 256 gigaflop versus 4 on today's current processors. Okay, and so on. And now I'm going to show you the practical, more or less practical demonstration. So I hope it's going to work because, oops, oh, I have a mouse. Basically, IBM is providing a cell simulator. I'm going to start it right now. It's a real cool thing because it simulates the whole cell processor with all SPEs and it runs Linux. And it runs on the Linux, I think only. So this is basically the console of the cell processor. This is the cell processor itself. I think I can raise the font a little bit. Oh God. Yeah, this arrow is coming every time. So we see, just ignore it. We see these 2 PPEs. So it's a dual cell, or it's a cell with at least 2 PPEs and 7 SPEs. I don't know where the other 8. Sorry, I don't know where the other 8 SPEs are gone, but yes. Basically, it works in the following. You can just, oh fuck, my start button is gone. So there should be a start button, but I think I should go down again. Sorry for this. So no, we have a fast mode. That's very interesting. So the fast mode enables or disables everything which is related to tracing the code. So timing, information, and all this stuff. And it's really going 10 times faster than the normal thing, the normal simulation. So. And you have to see, it's on my very, very slow notebook. It's only a Pentium system. And it's booting up Linux on the cell. This is the cell console output, and it's booting up a Fedora core, yeah. But, and another interesting thing is that they, on the web page, they say that, okay, it's just install it under Fedora core. But this is Gen 2, my notebook, because I don't like Fedora. You can just copy all the libs from the Fedora system to the any system else which is running a Linux kernel, and it works. So this is basically our cell. And the first thing I'm going to do on cool systems is this. Oh, sorry. Yeah, we see broadband engine. Oh, 2 gigahertz, cool. That's a very fast thing I have here. And yes, so that's the IBM code name. IBM basically calls the cell processor cell broadband engine, so CBE. And yeah, running with 2 of them on the simulator. And now I think I'm going very short. I have a small test program, which I will just compile. Okay, is this compiled? And I'll describe it later because because it takes very long to simulate. And there's also a very nice feature to interoperate between these two systems. There's a utility called call through, and you can just copy anything from the host processor to the simulated system. Oh shit. Oh yeah, source. So you see I have two binaries, one SPU S dot and one PPU S dot. So one for the SPU and one for the PPU. I'm making them executable and starting the PPU S dot. And now it begins simulating, and it takes quite a long time, I think 5 minutes. And in this time frame, I'll just show you the source code. So the PPU S.C is a very, very simple program. It's int main, of course. And then we have one big array, which is going to be calculated, a timing function, and between the timing functions and call to S dot. That's a dummy scientific function. Then we have another get time of day, a timing function, and an S dot SPU, and IDL join S dot SPU. So that's generated by the IDL language, the interface description language. That's really cool because you don't have to care for anything. You just program these S.SPU, call the IDL to generate you stub code, and you can use it like a thread or something. And then the second example is using two threads. So it calls the S.SPU the half of the data set. So the first parameter, where is it? Here, is here n, and here n half, and with another offset, of course, and it joins the two threads. So it should be, yeah, twice as fast. Now I'm going to show you the SPU S.C. It has to be a separate file because it's going to be a separate binary. Oh, sorry, I forgot something. So the PPU function is basically this one, which is calculate the normal S dot function. We have the array with four cascaded for loops, just to demonstrate a high load, and it's multiplied with a scalar. So everything is running from 0 to n, and now I'm going to show you the very fast. I'm going to show you the SPU code. So that's basically the same, but I have the, sorry, I have the vector. So I divide n by 4 and do this SPU multiplying the vector with the scalar. So it's just processing 4 things at one time, at one clock, and we see, oh fuck, there's a small mistake in the timing function of the simulator, I think. So this should take about 4 times this, sorry. Usually it does this, but if I do something else on the notebook, if I just set it on the load, then it behaves like strange. I think it's my mistake because I'm using the normal get time of day function for assessing the time. I should use something for the power processor to get clock cycles or this thing. But you have to believe me, if I would start it a second time, but we don't have time, we would see here 160,000, then 40,000, and then the next simulation is still running. So we are seeing here the SPEs which are assigned. SPE 6 and 7 is assigned. It's going to assign another SPE, but I think I'm going to finish now because they're looking angry. Sorry, thank you everybody for coming, and